Okay, so for the final talk of Oscar Randal-Williams series on chromatic approach to homological stability, was it an announcement you wanted to make, or? Oh, that was it. Okay, let's get started then.
Okay, so I've tried to explain this sort of paradigm that we're meant to start with a kind of homological stability question, meaning some collection of spaces that we're interested in, and we're meant to at least assemble them into an E2 algebra in sort of natural numbers graded spaces. And then because we're interested in homology at the end of the day, we're meant to linearize. In other words, take chains with some coefficients k and think of the result as augmented, maybe E2 algebra in chain complexes with additional grading, which is the n that's written everywhere. And then I try to explain in sort of starting, I mean, this is maybe how you get an R, but you can now just start with a general question of a general object in this category. I try to explain how under some modest axioms on this object, it always has this sequence of higher order homological stability theorems, which is the analog of the existence of Smith-Toda complexes in chromatic homotopy theory. So you can find the analog of a V1 self-map, then a V2 self-map, and so on. And then I tried to explain yesterday that the correct answer to the question of what is the secondary stable homology is given in terms of Bousfield localization with respect to the class of objects in the category of R modules that have a vanishing line of a certain slope. And both of those results are somehow general about any R, and they're sort of vague. They say you can always find a sequence of self-maps and so on. But if you have some specific R coming from some specific sequence of X's, how are you supposed to know what kinds of stability it should or should not have? So, for example, so how to know or how to tell what kinds of stability this example, say, of the X's, this example has. So, for example, usually R mod sigma has a slope 1/2 vanishing line, but sometimes it's better than a half. But for example, the mapping class group example has a slope 2/3 one. That's just true. So why? So why does, for example, I don't know, the symmetric groups has a slope 1/2 vanishing line, but the mapping class groups have a slope 2/3 vanishing line? Like, what feature of those examples is telling us that one or the other of these things should happen? And another sort of example is that for this red and blue points in the plane example there's no preferred sigma, and instead we have to cone off adding a red point, and then we have to cone off adding a blue point, and then this has slope 1/2 vanishing line. But what about this example tells us that we have to do two things before we achieve anything, and not one thing before we achieve anything, like we did in these examples? I mean, in some vague level, the thing that tells us we have to do that is that we've got red and we've got blue points. But what is the somehow general story that tells us to expect that we should have to do something like this? So I want to try to answer this question of what do you need to know about your example to decide what kinds of stability that example will have. And ideally, of course, you should need to know less than everything. So this axiom that I call the standard connectivity estimate said that the homotopy groups of the relative tensor product of the unit over R with the unit vanishes for D less than N. I just assumed that as an axiom, and I told you that many examples satisfy this axiom. So in other words, or rather in a picture form, the homotopy groups of this relative tensor product are supported on and above the diagonal in the N comma D plane. And what does this object mean, actually? As I said, everything in this business, once we're in the category of R modules, is automatically and invariably derived. So tensor product really means derived tensor product. In other words, it means the bar construction. So it's the geometric realization, if you like, of K tensor with K. And K is both a left and a right R module, so it has maps from K tensor with R tensor with K. And that has three maps from K tensor with R tensor with R tensor with K, and so on. Okay, so in other words, it's the two-sided bar construction where I treat K as both the left and the right R module. Okay, and that was using this fact that objects of this form come with the preferred augmentation. So I can think of the unit K as being a bimodule. So if I want to make this construction, the bar construction of an algebra kind of object R acting on left and the right module, I only need it to be associative. In other words, I need it to be an E1 algebra. I don't need it to be an E2 algebra. In other words, when I do this construction, I only use up an E1 structure on R. And that means if R was an E2 algebra, then I still have a residual E1 structure. So this only uses that R is E1. So I get a residual E1 structure on K tensor over R with K. So it's still an algebra. It just maybe doesn't have any commutativity properties anymore. So that's one thing you can do. But there's another piece of structure, which is you can sort of write in the following form. Let me artificially write this in a more complicated way, which is K tensored over R with R tensored over R with K. That's the same thing by cancelling the R with one of the R's. But now on the middle factor, I can use the augmentation. That's a map from R to the unit. So I can use identity tensor augmentation tensor identity, and that gets me to K tensor over R with K tensor over R with K. And then I can write that again in a needlessly complicated way by writing it as K tensor over R with K, tensored over K with K tensor over R with K. Fine. The upshot of this is that this object has a co-multiplication as well. Okay? And this is nothing but the very familiar fact that bar constructions always have a kind of Alexander-Whitney diagonal. And that's what it is. The way I've written it is sort of like some homotopy class of maps between these things, but this idea upgrades to an E1 coalgebra structure. You will believe me when I say that. So this gives an E1 coalgebra structure on this object. So in other words, it's like a Hopf algebra or a bi-algebra, maybe. Okay. So the homological groups of this object are distributed all in this region above the diagonal, but in particular, I can focus on the homological groups that are exactly on the diagonal. So this implies what I call delta R, which just means the diagonal homotopy groups of this object is a connected graded Hopf algebra. Just inherited by this co-multiplication and the multiplication that comes from the residual E1 structure. Okay. It's connected because everything, when you take the bar construction of something like this, the zero chains are just k tensor k, which is k. So it's all k in this degree. And then I say Hopf algebra out of habit. I mean, it's a bialgebra that's connected, and then it is a Hopf algebra in a canonical way, but that's not really very important. And the slogan is that every question you have about what kinds of stability R has is governed by this Hopf algebra. This governs the kinds of stability that R has in slopes up to 1, which is the regime in which I'm trying to say anything in these talks. And so what I want to try to explain in the next while is what does govern mean? I mean, what does this actually mean? Here's one thing it means. If I have an R and you have an R prime and they have the same delta, then our two examples have the same kinds of stability. It at least means that.
Sequences associated to such constructions, are they relevant to you?
So
Repeat the question.
that's all right. The question is, so there's many spectral sequences associated to all these derived constructions, and what role do they play? So the difficulty is, and the thing that makes it somewhat different in flavor to ordinary stable homotopy theory, is that we're interested in studying Rs for which we do not know very much about the homotopy groups of R. Like we're trying to prove qualitative things about them, like they have various vanishing lines and things like that, but we don't really know very much about them. So real kind of spectral sequences are sometimes useful as theoretical tools somehow, but they're not usually useful as calculational tools because we normally don't know anything about the input. So in fact, the next theorem I want to explain has a little bit of that flavor. So if I have a connected graded Hopf algebra A, I can consider it to be bigraded by putting it along the diagonal. Just like this one that I obtained was bigraded by putting it along the diagonal. I can consider it as such an object in Z graded chain complexes where it has no differential and it's diagonally graded. And then in that category, I can do the opposite of what I did here to make this Hopf type object. Namely, I can take the Kobar construction of it. And that's some very convenient notation that my student Kelly Wang invented, which is that I'm going to call it lowercase a. Kobar capital A. And a Hopf algebra is an E1 algebra and an E1 coalgebra. When I take Kobar of it, just like I did here, I turn the coalgebra structure into another algebra structure. So it becomes an E1 tensor E1 algebra, aka an E2 algebra. So whenever I take Kobar of a Hopf algebra, I get an E2 algebra in whatever context I'm living in. And in fact, you will end up, oh, I've erased it now, but you will end up exactly in this category that I said.
Those arrows and stick ours in the.
I mean, of course, you don't, yes, and heuristically, you do that, yes. So it's a Hopf algebra, so it has a multiplication already. To make cobar, I don't use the model, I just use the coalgebra structure. So, and cobar of a coalgebra always has a multiplication, but now I have two multiplications, yes. So this is constantly using so-called Dunn-Lurie additivity, that an E1 algebra in E1 algebras is an E2 algebra, and vice versa. So you're constantly using that to go between these 2 points of view. What is this in a kind of down-to-earth way? It's sort of exactly the opposite of what it is up there. It's the totalization of the co-simplicial object, which looks like K tensor K. That maps to K tensor A tensor K using the two coactions of A on K, and so on. That's what cobar means. And by definition, the homotopy groups of this have a name. Pi nd of this object, they are cotor of the Hopf algebra capital A. And because I've put these things in this diagonal by grading, the degrees need some thinking about. But what you get is that. So you get the n minus d derived functor of cotensor product in internal grading n. Okay. So this is somehow Tor of algebras is somehow the homology theory for associative algebras, and this is the homology theory for coalgebras. So this is coalgebra homology of A. So incidentally, from here downwards, I've just explained an enormous supply of examples of E2 algebras that satisfy my axioms. As long as A also has finite type, then this cobar will be supported in the first quadrant, so it will be connective. It will be finite type if A has finite type. And if I take its bar construction, of course, I get A back, capital A, which is supported along the diagonal, and in particular is supported on and above the diagonal. So it satisfies the standard connectivity estimate. Okay? So the point of saying this is that cobar of any ordinary finite type Hopf algebra gives examples of everything I said in the last 2 days. And in particular, all the theorems I talked about in particularly apply to cotor or X over Hopf algebras. And in many cases, the theorems I talked about are known theorems in that context, and they're theorems typically of Palmieri, who studied a lot about doing homotopy theory in comodules over a fixed or Hopf algebra. So truncation to the diagonal gives me a map from this object to just its diagonal part. That's just the analog of taking connective covers. And in fact, it is taking connective covers in a certain T structure. But then I can take cobar of that. So if I take cobar of bar of capital R, I just get capital R back. And on the other side, I get what is going to be called lowercase r, and it just means cobar of this diagonal Hopf algebra. Okay? So this gives me a map from any E2 algebra that satisfies my properties to another one called little r, which they will have very different actual homotopy groups or homology completely, but they will have exactly the same kinds of stability. And then you can work out what those kinds of stability are by studying little r and just doing ordinary homological algebra in co-modules. That's the point. And I want to formulate what it means to say they have the same kind of stability. So here's one formulation of that. So if lambda is less than or equal to 1 and M is a finite R module, then M has a slope lambda vanishing line if and only if its base change to little r does. So I can test vanishing lines by base changing down to little r. That's what the first part says. And the second part says, if lambda is now strictly less than 1, and M is as above, and phi is an endomorphism of M, whose slope is exactly lambda, then we can test if this endomorphism is nilpotent or not by base change down to the little r. So then phi is nilpotent if and only if, when I base change it down to this kind of module, is nilpotent. And sorry, I missed an axiom here. This M, let me do it in pink so it's not overlooked. M should have a slope lambda vanishing line. So this endomorphism should be parallel to the vanishing line of M.
Is phi the actual self map?
Yeah. Right. So M is meant to satisfy the first part. So it has a slope lambda vanishing line. And I've got an endomorphism phi parallel to that vanishing line. And I want to decide whether or not that endomorphism is nilpotent. Then I can decide that after base changing down. Of course, the forwards direction is obvious. And the backwards direction is useful. Yes.
Does that means like analogy with theory?
Yes.
No, so why are bad and
So, right, the question was, in the analogy with chromatic homotopy theory, I asserted that there's no good analogy with Marva K theories and maybe with MU and stuff like this. And so why is little r not a good analog of that? In some sense, this is saying, you should think of this as being very much like the nilpotence theorem. It's saying there's a homology theory called little r that detects nilpotence. The thing is, it only detects nilpotence for endomorphisms parallel to a vanishing line. It doesn't detect nilpotence in general. So that's why it's not quite the same. But this is good enough for the things you want to do, because the things you want to do is decide, when I've got a proto-stabilization map, do I really need it or not? Because if it's nilpotent, I don't need to think about it. I can just ignore it. So this lets you make that sort of decision. But other than that, yes, this is of course meant to be analogous to something like a nilpotence theorem. It's saying there's a certain homology theory little r on capital R modules that detects nilpotence in some limited sense. And in fact, the proof is very much of that flavor. Namely, you study the little r-based atom spectral sequence on capital R modules. No, there's one thing. There's one little r associated to capital R, and it's good for every given slope up to 1. That's true, but it's only good for endomorphisms parallel to vanishing lines of an object. Yeah. So you don't have to pick. You don't have to pick a different homology theory for each slope. Right, I mean, this is obviously not the proof, this is the proof idea. Because the map that assigns to phi, the endomorphism phi, this endomorphism, is obviously the edge homomorphism in the atom spectral sequence. And so what you want to show is you want to say, if this map is nilpotent, then we may as well take an iterator phi so that this map is 0. That means that the map phi has strictly positive Adams filtration with respect to the theory little r. And that means if you take further iterates, it gets even bigger Adams filtration. And you argue with vanishing lines that once something's got big enough Adams filtration, it's in the region where something is 0. Okay, and the vanishing line is established using the assumption on the vanishing line for M. Yeah.
These vanishing lines, once you pass to the Adams spectral sequence, do these vanishing lines appear in the spectral sequence itself?
Yeah, so that you, I mean, right. So the question is, how do the vanishing lines on the module relate to the vanishing line in an Adams spectral sequence? Yes, so of course, everything has at least one more grading to what most people are used to. So this has a vanishing line in the n, d plane. And to make arguments about Adams filtration, you need to establish vanishing lines in the something, filtration plane. And so the quantitative work is translating between what this tells you about vanishing lines in the Adams spectral sequence. So this is using the Adams spectral sequence in a very theoretical way. The homology theory little r is not of Adams type, meaning little r tensor over capital R with little r is not little r flat. And so you have no hope of explaining what E2 of this spectral sequence is. You just use it from the E1 page onwards, and you just use whether things are 0 or not 0. You don't use it to actually calculate anything. So let me just say, so this this meaning this sort of point of view can be used to argue that if I've built a kind of Smith-Toda complex that's most efficient, which maybe means for the vanishing line that it has the fewest alphas or something like that, then when I base change it down to little r, it is 2. And of course, the way you use that is backwards. You say, I want to know if I needed to actually use alpha r or not. And so I base change down, and I say, for this object here, when it goes up to alpha r minus 1, if alpha r was nilpotent, then I didn't need to use it down here, but then I shouldn't have needed to use it on capital R either, because it was also nilpotent there by the second part. But it's kind of technical to make a real argument about this. So this sort of, so with some more work, we can sort of lift Smith-Toda complexes for little r to ones for capital R. That's a bit of a vague statement, but roughly speaking, if you could build an object of this kind, then the alphas over here will have somewhat different meanings to the alphas here, but there will be the same number of them and they will have the same slopes and things of that nature. The ones over here might be, in some vague sense, large iterates of the ones over here. So the upshot need to understand stability phenomena for things like Kotor of Hopf algebras. And as I said, Kotor over Hopf algebra or Kobar of Hopf algebras embeds into my setting, so you cannot possibly simplify beyond that. Right. Those are examples of E2 algebras and so on. Yeah.
With the Smith-Toda complexes, this is something exists in the computing examples, but it's not how you construct. Or is it?
The best way to think about this, I mean, I haven't talked about an argument for proving this. I sort of alluded that it happened in this filtered setting, and you somehow. The way it works there is that there's sort of proto alphas that exist, and the question is, are they sort of permanent cycles? And then they're always sort of non-nilpotent on the associated gradient, but it could be that the permanent cycle that represents them is for some reason nilpotent on the object itself. Like as filtered maps, they're non-nilpotent, but you don't really care about them as filtered maps. You only care about them as underlying maps, and then they could be nilpotent. So you sort of always have a provisional list of alphas, and you really want to know which ones you can ignore. And the correct statement here really is that you can ignore the same ones for little r as you can for capital R, in some sense. Okay. So I wanted to talk about some examples of things. So there are not many examples where the stability of algebra is completely known. But you don't need to know it completely. You can, if you have partial information, then you can run the game partially. So you don't need to know. Yeah.
Restrictions on R.
I mean, there's my usual three axioms that it should satisfy. I mean, the main one is it should satisfy the standard connectivity estimate, meaning its bar construction should be supported above the diagonal. Yes. And then finite type. So there's not many examples where it's completely known, but you don't need to know it completely to run the game partially. So you can often use partial information to learn something. Let me tell you some examples. Maybe the first one is just a free E2 algebra on one generator called sigma. This is the same as doing chains on configuration spaces of n points in the cube. With whatever coefficients. So it's just doing stability for configuration spaces in dimension 2. And of course, this is a super degenerate example because, as I've said many, many times, we just know the homology completely, but let's run the game anyway. So it's a general fact that when you take a bar construction of a free EK algebra, you get the free EK minus 1 algebra on the suspension of the generators. So here you get the free E1 algebra on a 1,1 cell whose name is sigma bar. E1 algebra is also known as a tensor algebra. So in this case, so this has all its pi star on the diagonal. Right, it's a tensor algebra on a class of degree 1,1, which is on the diagonal. So when you go taking powers, it's also on the diagonal. So this stability Hopf algebra in this case is just a tensor algebra on one generator. And in this case, the simplification of comparing capital R to little r is no simplification at all, because this object is already just only on the diagonal. It is just an ordinary Hopf algebra. And so this capital R is in fact just co-bar of a tensor algebra. And we haven't simplified at all. It is just a primitive object in the story, and you have to deal with it by algebraic means.
You get the co-product just because there can't be many different co-products in themselves.
The way I've said it here exactly, right, this is a very good point. The object is a Hopf algebra. I gave you this formula for what the coproduct is, using this, write it as R tensor of R with R, blah, 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 and use the diagonal. In practice, what you do is you know the algebra structure well, and you intuit what the co-algebra structure must be. And in this case, that's very easy. It's a tensor algebra, so it's generated by one element, sigma bar. So I just need to know what the coproduct of sigma bar is. But sigma bar is the class of lowest degree, so it has to be primitive with respect to the coproduct. And then you know what the coproduct is on everything else by multiplicativity. So in fact, as a coalgebra, it's somewhat more complicated than this. The dual to the tensor algebra is I guess it's an exterior algebra times the divided power algebra. So it's somewhat complicated, and that's why, we're really interested in its nature as a coalgebra when we take the cobar construction. So as a coalgebra, it's moderately complicated, and that's why the homology of braid groups is moderately complicated, because its cotor are an actually quite complicated coalgebra. Because the divided power algebra is actually quite complicated. It's a compact name for a quite complicated thing. So that somehow explains why homology braid groups or of these configuration spaces has quite a lot going on. But that's a situation where we know it completely. Another situation where we know things fairly completely in this regime, I rush to add before somebody objects, is if we do general linear groups over a field. If F is a field that's not F2, but any other field, it can have characteristic 2, it just can't be literally F2. Then we do know the diagonal Hopf algebra, and it's just an exterior algebra on one generator. This is a fact. I guess that is due to Soren Galatius, Sander Coopers, and myself. And I don't explain why that's true. I want to explain what it means in the story that I'm telling in these talks. So little r is not so bad. It's cobar of an exterior algebra, an exterior coalgebra, sorry. Now the dual coalgebra to an exterior coalgebra is actually just also an exterior coalgebra because there's not many choices. So this is dual to, like the homological groups is dual to like taking Tor over an exterior algebra in one generator, and that's a polynomial algebra in one generator. And what you discover is that this is just equivalent to the polynomial algebra on sigma. Now I put it to you that this has incredibly good homological stability properties. If I take the mapping cone of multiplication by sigma, I get a one-dimensional vector space, and a one-dimensional bigraded vector space has a vanishing line of any slope you want. You just put the offset so that it doesn't cover the line. So this has so R mod sigma, the homotopy groups of R mod sigma, is just K in by degree 1, 0, and is 0 otherwise. And so the point of the story is that this ridiculously complicated example, even though it's ridiculously complicated, it has the same kinds of stability as this almost trivial example. In particular, it has very good stability. In particular, this has a slope 1. I mean, it has a slope 1,000,000 vanishing line as well, but in particular, it has a slope 1 vanishing line. And then by the first part of the theorem that I've now had to erase, that implies that R mod sigma has a slope 1 vanishing line 2. Okay.
You don't know that it has a slope, no.
No, because the theorem lambda had to be for the thing that detects connectivities or vanishing lines, it had to be at most 1. Yes. So this is not, I mean, the paper that did this also proved that they have slope 1 stability, a different way. But this is a hyper efficient way, I think, of going between this essential calculation and what you wanted to know, I think.
But here you don't know the offset at all.
No, it has a slope 1 vanishing line through this point. Ah, I see. Maybe I stated the first part of the theorem inefficiently. You can take the same line. In the theorem that used the Adams spectral sequence, it's not just the slopes go back and forth. For the connectivity, you can take the same line. Yes. So it has a slope 1 vanishing line going through I guess it's just 0, 0, in fact. Yes, going through the origin. Right, sigma is not there because you've killed sigma. Yes. So as I say, the conclusion is not new. It was also in the papers that I wrote with Songalators and Santa Coopers, but this is a different way of interpreting the basic calculation as leading to the answer. Yeah. So for F is F2, we don't know what it is. My student Kelly Wang is working on that at the moment, and it's very interesting. That's all I will say. Sorry? Yes, it's much more complicated. Yeah. But that's some work that she's doing at the moment, so I don't want to say too much about that. It's outrageous that the field F2, specifically F2, is special among all fields. And I'll tell you what the reason is. For a general field, take the field and take the covariance for the units in that field. For every field apart from F2, that's 0. And for F2, there's not so many units, and you get F2. And that's actually what distinguishes F2 from all other fields.
There's no Morava-K theory, but are there formal group laws?
No, I don't think so. I don't think so. Right. So I wanted to tell you, maybe I'll finish by doing a kind of a more sophisticated kind of example of this nature, where you take something that you know about the stability Hopf algebra, in a case where it's more complicated than this, and you do something with it. And this is what happens if you take general linear groups over the integers. And let me do it with F2 coefficients. So this has, and again, I've just asked you to believe this assertion. This is what its stability Hopf algebra looks like in degrees up to about 3. It has a unit. It has a class called sigma bar, which is the same as the one from before. It has a class sigma bar squared. It has the class sigma bar cubed. And it has another class called rho bar. And it probably has other stuff as well, but it has at least that in degree 3. And then we don't know what happens up there. And this is a Hopf algebra. Well, the multiplication is, I hope, clear. Sigma times sigma is the thing called sigma squared. Where the co-product, I mean, sigma bar has degree 1, so it has to be primitive. But let me write it anyway. And the interesting thing is rho. So the co-product always has the terms whatever tensor 1 plus 1 tensor whatever. But this also has the term sigma bar tensor sigma bar squared. Okay? And it does not have the term in other order. In particular, this is not a co-commutative Hopf algebra. So in particular, so this, if you're not familiar with this co-algebra business, this is what's called being primitive. And is the co-algebra version of being indecomposable in an algebra. It's saying there's no two things you can co-multiply to co-get it. Because we're working characteristic 2, and we're in a bialgebra, so the co-product is a multiplication of algebras. That's what it means to be in a bialgebra. So if I want to calculate the co-product of the square, I can compute the square of the co-product. But because we're over F2, squaring is linear. So we just get this. So this is also primitive. And generally, whenever you take squares of primitives, they'll be primitive. And in fact, here the multiplication happens to be commutative. And if you take commutators of primitives, they'll be primitive as well. And just like when you're studying homology of algebras, so Tor1 of an algebra measures indecomposables for that algebra. And similarly, Kotor1 of a coalgebra measures is primitives. So we have, because we know some primitive elements in the coalgebra, then we know some elements in the homotopy groups of cobar of this coalgebra. So we have what I call sigma, which is the class represented by sigma bar in Kotor1 delta R, F2, F2, and it will be in grading 1. And that corresponds to pi10 little r under this isomorphism that I said when we're doing the homotopy groups of cobar are just Kotor of the Hopf algebra. So that's one element that we know. There's another element. So this sigma bar squared was also primitive. So it also gives a class in Kotor1. It now has grading 2, and that will correspond to pi21 little r. If you like homology operations, and if you're doing EK algebras, you have to like homology operations, then this is the class called Q upper 1 of sigma. It's the first dilateral operation applied to sigma. It might be more familiar to call it square lower 0, maybe is what Hopf algebra people call it, but it's the first power operation, and it just corresponds to doing the Frobenius map to the entries in the cobar complex. It is what we did here to that. So that's something. So the fact that the co-product of this row element, I mean, the outer terms don't matter, they're always there, but the fact that it has this in it tells you that this element times that element is a co-boundary in the cobar complex. Namely, it's the co-boundary of row bar. So this implies that sigma times Q1 sigma is 0 in wherever it lives. I guess it's going to be Kotor2, F2, F2. I guess it'll be in grading 3, and it will be in then pi 3, 1, a little r. That's exactly what it means for something to arise as in the coproduct of something else. It's saying in the cobar complex, it becomes a coboundary. If there were many terms here, then it would be the sum of them was a coboundary, but here there just happens to be one non-stupid term, so it just tells you that that is 0. So with this little r, we've started canonically naming some elements. We even know some relations that the elements satisfy. And we can now start, and the whole thing is a E2 algebra, so it has homology operations, these Q1 that I've already used. So you can apply the dialectical operation Q2 and use the so-called Cartan formula to this. And I'll write it out and I'll assert some things. Okay. If you do this correctly, then this is the formula that you get. The thing that's maybe not completely obvious, but if you look at the way the degrees work, and if you reindex your Kotor the way that most people are familiar with, you'll discover that this is automatically in a group that's 0. So you just get this identity. So what is my purpose in doing this? The advantage of working in this purely algebraic situation with cobar or Kotor of a Hopf algebra is that you can then do purely algebraic things. And what I want to do is filter this Hopf algebra by powers of its augmentation ideal. This is in the region of like the May spectral sequence or the Ivanovsky spectral sequence for cohomology of Hopf algebras. So filtering this by powers of its augmentation ideal gives sort of May slash Ivanovsky spectral sequence, converging to what I am interested in, so Kotor over this algebra, and it converges from Kotor over the associated graded of the filtration by powers of the augmentation ideal. And of course, there's some secret other grading that I won't write. And the point of filtering by powers of the augmentation ideal is that the associated graded is always a primitively generated Hopf algebra. And you just know what Kotor of a primitively generated Hopf algebra is. And let me just tell you what the answer is. It's a polynomial ring. And of course, we can only say so much because I only told you a little bit of information about this Hopf algebra. And so what we can say is what it looks like in low degrees. So it's got polynomial generators sigma and Q1 sigma, and then it has generators of slope at least 2/3. That's what you get if you take this table, which I've had to erase, of what delta R looks like in low degrees. We knew it, roughly speaking, up to degree 3. In fact, in degree 3, there was an ambiguity. We knew it for sure up to degree 2. And that corresponds to knowing what happens to all the generators of slope at most a half. And the first thing we don't know is slope 2/3. And remember, this is this homotopy groups of the object little r. So there's now a very easy calculation you can do, which is if I want to know the homotopy groups of this object, I can run the module version of this spectral sequence, and it will start with a polynomial ring with these two generators missing, because I've taken the quotient by them. They are gens of slope at least 2/3, and it converges to this. And we don't know what the generators are, but if they all have slope at least 2/3, then all products of them also have slope at least 2/3. So this whole thing lives above the line of slope 2/3, and then whatever happens in the spectral sequence, this must also live above the line of slope 2/3. So we end up saying that this vanishes for d less than 2/3 n. So I want to do one more. This is not really the question about, this is some sort of question. This is some sort of Smith-Toda type complex that has a slope 2/3 vanishing line. So from some point of view, it's a perfectly good answer. But using the calculations on this board, we can improve it. And the reason, let me say it in words first, the reason is, here we killed sigma, which is what we're really interested in. Then we killed Q1 sigma. This relation, the fact that that is 0, says that when you work mod sigma, Q1 sigma is nilpotent. It has order 3. So actually killing it is not super different from killing its Q power, which is not super different from doing nothing at all. So I want to explain how you implement that. So you can say, oh, I just erased it. So the identity Q1 sigma cubed is sigma squared of something. It doesn't really matter what the something is, but it happens to be this. Means that Q1 sigma multiplication by this is null on the object R mod sigma. So you can then make the following line of reasoning. R mod sigma is a retract of R mod sigma and the 0 map. If I cone off the 0 map, I have the original thing as a retract of it. But this has a filtration with associated graded 3 copies of R of this one down here. So it has R mod sigma, Q1 sigma, and then I think it has a 2-1 suspension of the same, and then I think it has a 4-2 suspension of the same. So at the level of approximating things, what's 0 and what's not 0, this object has a Van der Waals of slope 2/3, and this object is built out of 3 of those with some little shifts involved. Namely, you put one of them at the origin, and put a line of slope 2/3, then you put one of them at 2,1, and put a line of slope 2/3, and you put another one at 4,2, slope 2/3. And obviously the third one is the worst one. You learn a little bit down here, but roughly speaking, this line is the worst one. And what you learn is that pi nd of R mod sigma vanishes for d less than 2/3 n minus 1 if you go through if you're careful with the lines and so on. It has a little horizontal offset that comes from the fact that it's not through the origin, but through the point 4,2. So in other words, i.e., GLN of Z has ordinary stability of slope 2/3. And this is also not new. This is a theorem of Cooper's, Miller, and Past. But the way you go from the essential core calculation, which is what does the stability Hopf algebra look like in low degrees, to the conclusion, I think changes very much in style once you adopt this Hopf algebra point of view somehow. Like you realize that you're just doing calculations in low degree cohomology of Hopf algebras, and you play games in the Kobar complex and stuff like that. So one still has to do the hard work. Given some example of some x's, you still have to do the hard work of proving that the space of ways of splitting them up is as highly connected as I want. So that's this standard connectivity estimate. And that is always super adapted to the example that you're studying. If you're doing mapping class groups, then you have to think a lot about arcs on surfaces and so on. And if you're doing general linear groups, you have to think a lot about splittings of modules into pieces and things like that. The point I want to make here is that the next piece of work you should do is to study what the homology groups of those complexes are when they don't vanish, in the degree above where they vanish. That's roughly what this stability Hopf algebra is the collection of all of those homology groups of all these splitting complexes in the degree above where they vanish. And those happen to assemble into a Hopf algebra, and you have to understand the structure of that Hopf algebra if you want to prove things about that example. And as I've said, there's very few examples where we know it completely, but it seems to be quite a rich thing. Maybe I'll stop there. Thank you for your attention.
Any questions?
So just maybe this is sort of obvious from what you've said, but just to make sure, just to see if I understand. So this sort of shows that the reason that am I correct to say that this shows the reason coding off nilpotent elements doesn't really matter is because it only changes the shift, not the flip?
But then, of course, if you actually want to know what the shift is, then you have to deal with how nilpotent those nilpotent elements are. Yeah.
So you have to find a
reason it's nilpotent, like an explicit reason. And in this case, I think this is the smallest power that induces 0 on R mod sigma. There's some small subtlety here for people who like homotopy theory. If you kill an endomorphism sigma of an object, then the endomorphism sigma of that object is not 0, but sigma squared is 0. And it's lucky here that it's divisible by sigma squared, so it induces the trivial map on R mod sigma.
Anyone else? No one in the chat? Okay, then let's thank Oscar. Oh, dat was
Do you get good if in theory it occurs that delta R is a Cazoli algebra?
Sorry?
there could be a chance that you obtain a causal algebra, for example, in your when you got this exterior algebra and polynomial algebra.
Right. There could be. I don't know that happened. I mean, I have some very toy examples, but that happens.
Okay.
I mean, for example, you can make toy examples. You can start
Yeah.
with any Hopf algebra that happens to be causal as a coalgebra, and you can take cobar of that.
And would this imply anything really good?
I mean, it certainly can't hurt, I suppose, but I think that the sort of things you want to know are a little bit orthogonal to actually computing the groups, because all this helps very much if you want to actually compute what happens. Here, you're sort of more interested in slightly more qualitative things. I mean, it may help for that as well, but I think it's it might be overkill for the kinds of questions that you want to answer.
Okay, maybe now we can thank Oscar again.
Yeah. Not yet. Not yet. Maybe so. It will be done by solution.
It's done. On my horizon, let's see if that's the talk proceeded. Never mind. Okay, to see you. Yeah, sure. If I'm exactly more the next day, you'll be hanging out.
I mean, I'll be taking over.
Send you an email. If we sit down to chat, it's still, it would be nice to think about how different work feed in.
Yeah.
Maybe